Okay, so for today, I will try to continue with the discussion on the problem example of the wedges. Okay. So this is the first problem that we will discuss today. And for today, we will discuss several problems. And most of it, I will try to finish it until the end, but some of it, maybe I will just give a general way how to solve it without solving until the end. Okay. Can you see the problem here, guys? Hello?
Yes, sir.
Yep. Okay then. For this particular problem, it's quite standard, right? As usual, you have to analyze the wedge and you have to analyze the weight as well. So the first thing that you're supposed to do is to draw the free body diagram of the weight and the wedge. Okay. And one thing that you have to be very careful here is it has two different. The problem has two different friction coefficient. Okay. So here it has the between the block and the horizontal surface. So at this particular surface, the static coefficient of friction is 0.6. And then between the both wedge surfaces, this and this, both are 0.3. So it's slightly different. Okay. So the first thing that you're supposed to do is you have to draw the free body diagram as usual. Okay. If you want to draw the free body diagram, then this is the free body diagram of the wedge. Okay. We have the force P there. And beside that, we have a normal force as well as the friction force. Okay. Here we have the normal force, normal to the surface. Remember, normal force is always normal surface. Normal force 1. And because P is going down, so the friction force is supposed to be to the opposite of that. Friction force 1. Then on the second surface, we have normal force as well. Normal force 2. And we have friction force 2 going up. Okay. But the question here is the value of the P in order to move the block. So in this case, right, you have to remember that as usual, friction force, okay, because it's the least force needed to move the wedge and the weight as well. So it's supposed to be in the impending motion condition. So this one, F1 here is supposed to be mu s multiplied by N1. And the mu s there is supposed to be 0.3. So 0.3 N1. And F2 there is supposed to be 0.3 N2. Okay, so basically in the first free body diagram, okay, we have three unknowns, P, N2, and N1. Then in the second free body diagram, we have to draw the weight, this one, the weight. Okay, if we want to draw for the weight, if you want to draw for the weight, this one, yeah. Okay. There will be weight of 500 kilogram multiplied by G. Okay, and what else that we have there? There will be normal force here, normal 3. And because when we push the wedge in like that, the weight will move to the right. So the friction force will be going to the left. Friction force 3, like that. And on this particular surface, it will be action and reaction with this particular surface. So there will be a normal force going to the right. And then friction force. Okay, friction force going down. Friction 2, like that. So this is the whole free body diagram, right? This is the whole free body diagram. And as usual there, F2 is supposed to be 0.3 of M2. Okay, F2 is equal to 0.3 N2. And then here, F3 is supposed to be 0.6 of N3. Why it's like that? Because of this. The friction coefficient there is slightly different. Okay. Remember here, in the second free body diagram, okay, we only have 2 unknowns. The first one is N3, and the second one is N2. Okay, so the weight is known, so we can solve for the problem using sigma fx equal to 0 and sigma fy equal to 0. Okay, if you want to use the sigma fx equal to 0 first, then what we will have here is it will be N2 minus F3 supposed to be equal to 0. But remember the F3 there, we're supposed to put it as 0.6 of N3 equal to 0. That's why N2 will be equal to 0.6 N3 like that. That's the first results, okay, using sigma fx equal to 0. Then using sigma fy equal to 0, okay, if I assume that the G is equal to 10, then yes, the weight here is 5,000 Newton. Okay. What we will have there will be N3 minus F2, which is 0.3 and N2. 0.3 N2 minus 5,000 Newton equal to 0. Okay, equal to 0. As you can see here, it involves N3 and N2 as well. But remember, we have here N2 is equal to 0.N2 is equal to 0.6 N3. And the one that we need is the value of N2. Okay, so I will replace N3 with N2. So here N3 will be equal to 0. of N2. Okay, so I will replace that. Then what I will have here is 10/6 of N2 minus 0.3 of N2 minus 5,000 Newton equal to 0. Then I can calculate for N2 there. Okay. So the value of N2 there, okay, 10/6, sorry, 10/6. Okay, 5,000, 1.36666, 5,000 5,000 divided by that. Also, the value of N2 will be around 3,658.5 Newton. Correct, right? Anyone here is following my calculation? Hello?
Yes, sir.
Yes,
Is it correct?
Yes, sir.
Okay, then. After we find out the value of N2, then we can go to the first free body diagram here to solve for P. Okay. We find the value of N2, 3,600 something, and then we can find for P and N1. Okay. So for this one, then sigma fx equal to 0. In order using sigma fx equal to 0, what we will have is N2 minus N1 cos 5 degrees, then minus, then plus 0.3 N1 multiplied by sin 5 degrees. Okay, equal to 0. Using this, we can calculate for N1, because N2, we already find the value, 3,658, right? Anyone here can help me to find out the value of N1 here? Hello?
Let me put the calculator, sir.
Zero.
$3,771.5, sir.
3,000?
771.5.
3,771.5 Newton forever. Correct, right? Okay. Then After that, we can calculate for the value of P using sigma Fy equal to 0. Okay, using sigma Fy equal to 0, then what we will have is P minus F2, which is 0.3 of N2, okay, minus F1, which is F1 cos 0.5, cos 5 degrees, which is the same as 0.3 N1 cos 5 degrees. Then minus N1 sin 5 degrees equal to 0. Okay. Using that, we can find for the value of P. Sorry. What is the value of P there using this calculation? Hello, Nuki, can you help me to find for the value of P here? Or anyone else here? Azir?
Working on it, sir.
2,553.4, sir.
2,550.4.
53.4, sir.
Or 53.4. Okay. So that's the value of P there. So that's the way to do it. So this is the one of the most basic. Okay, thank you, Sam. Thank you for helping me for this calculation. And Matthew, yeah, by the way, this is one of the simplest problem. Okay, this is one of the simplest problem in wedges, okay, in wedge. So you can see that we have to check for the mass and we have to check for the wedge as well. So we have to draw at least 2 free body diagram. In this case, the free body diagram of the mass and the free body diagram of the wedge. And one thing that you have to make sure from the beginning is the value of the coefficient of static friction. So as you can see here, this particle surface has 0.6 μs. This two surface has 0.3 μs. So that's the thing that you have to be very careful from the beginning. Okay, so as you can see, the way to draw it, you can draw it like this. Okay, normal force and friction force separated, but remember that the friction force there, it depends only on the normal force and the friction coefficient. The friction coefficient is known from the beginning, so it's only depend on the normal force. So we only have one unknowns for its set of normal and friction force. Okay, so you can draw it like this, or you can draw it like this. So it's basically more or less the same. Okay, this one as well. It's the same as this one. The result's supposed to be the same, whatever you do. Okay, but if you want to draw it like this, the first thing that you're supposed to calculate is the angle phi. The angle phi there depends on the mu they use. So for this surface and this surface, we have to use mu of 0.3. That's why the phi there is a arcus tangent of 0.3, which is the same as 16.7 degrees. Here, phi 2 there is supposed to be depending on the friction coefficient of that part. The friction coefficient of that part is supposed to be 0.6. So the phi 2 there is supposed to be arcus tangent of 0.6, which is 31 degrees. Okay, so the results are supposed to be more or less the same. There are several problems here that we can try to solve. But for this one, I think we will try to analyze it just a little bit only. Okay. If you have this kind of problem, okay, determine the force P required to force the 10 degrees wedge under the 90 kilograms uniform grade, which rests against the small stop at E. Okay. The coefficient of friction for all surfaces is 0.4. Okay. How can we draw the free body diagram? The most important thing here is you have to know exactly where's the direction of the normal force and where's the direction of the friction force. Okay, remember, if you want to draw the direction of the normal force, it's supposed to be perpendicular to the surface. Okay, perpendicular to the surface. Normal force is always perpendicular to the surface. Friction force is always parallel to the surface. So in this particular case, if we want to draw the free body diagram of the wedge, this is what we will get later. Because we have 10 degrees wedge here. Yeah. So, okay, because we have 10 degrees wedge there. Okay. And then the force P is following the angle of 10 degrees as well. So it's supposed to be parallel with the slanted surface. This is the force P there. Okay. Beside that, what we have here supposed to be the normal force and the friction force at the wedge. Okay. I think I will point out one of you to help me to do this. Adam, can you hear me, Adam? Hello? Adam? Adam Putro?
Morning, sir.
Now, please help me to draw the free body diagram of the wedge. We have two surfaces, right? Adam, the first one is supposed to be the bottom wedge, and the second one is supposed to be the top wedge. Okay, at the bottom wedge, what is the direction? What is the direction of the normal force? Hello, Adam?
Perpendicular
To the
surface.
To this particular surface then, right?
The top surface, yeah.
Nah, the bottom, I'm asking you the bottom one. Okay, so this one supposed to be perpendicular to the bottom surface like this, right?
Yeah.
So it's supposed to be N1. Okay, we name it as N1. And how about the friction force? Hello, Adam?
To the left, sir.
To the left and parallel to the surface, right?
Yes.
Okay. To the left and parallel to the surface. F1. Okay. F1 is supposed to be what value in terms of N1?
Uh, 0.4 times N1.
Yeah. Correct. 0.4 times N1. Okay, now the top surface. Where's the direction of the normal force?
Are we considering the box or the top surface of the wedge?
What do you think? What do you think?
I think the wedge itself, sir.
Yes, correct. It's supposed to be. We're supposed to use the wedge. Actually, it's not necessary we have to use the wedge or we have to use the mass like that. But when we think about this, the friction between the crate and the wedge, okay, you can see right, that the crate, the friction at the crate only happening at one particular point. But at the wedge, okay, because of the movement, it's supposed to be happening at the surface. So I mean, the movement will be happening at the surface like that. But at the crate, the friction will only happening at one particular point, right? So basically, we're supposed to use the one that have a surface there. The one that having a movement on a surface is supposed to be the wedge, right?
Yes, sir.
Yeah. So in that case, we're supposed to use the wedge surface as our reference. In this case, we have N2 like this, perpendicular to the wedge surface. Because N2 is perpendicular to the wedge surface, then the friction force as well is supposed to be parallel to the wedge surface, right?
Yes.
Okay, and where's the direction? To the right or to the left? The movement is going to the right, right? So the friction force is supposed to be to the left as well. Friction force 2 is supposed to be, the value is supposed to be 0.4 of N1 as well. Okay, do you get it?
Is it N1 or N2, sir?
Sorry, N2. This one is supposed to be N2, yes. Thank you. Okay, so for this one, we have to use the surface of the wedge. Why? Because the wedge, the contact on the wedge will be on the surface, but the contact on the crate will be on a point like that. Okay, and then if we want to draw the free body diagram of the crate, okay, if we want to draw the free body diagram of the crate, and you can see there that the crate is having a 5 degrees angle there. Okay. What you have to do here, so remember at A, there will be some kind of pin joint there. And then we have weight of 90. We have weight of the 90 kilogram there. Okay, assume that is using 10. We assume that it's using 10 meter per second squared. Okay, then now my question is, what are the forces that we have on the crate there beside the 900 Newton?
You have 900 newtons going downwards and then N2 going upwards at the left side, left bottom side.
This one, and 2 going upwards. What else?
And the friction F2
Going
to the right.
to the right. Remember, to the right, and it's not making any angle. Okay, so it's supposed to be to the right. So because it's supposed to be action and reaction with the it's supposed to be action and reaction with the one you have here.
Wedge, yeah.
So F2 is supposed to be 0.4 of N2 going to the right. Okay, what else do we have there?
At A, do we have N3 or is it like AYAX?
Yeah, it's up to you. You can just put it as AYAX as well. AYAX. Okay, for this one, in order to solve it, because we have the length here and the length here, the height and the length, right? So there will be 3 equations that we have for this particular crate. Okay, the 3 equation will be, so this one is the first free body diagram and this one is the second free body diagram. For our second free body diagram, we will have 3 equations. The first equation is sigma fx equal to 0. Sigma fy equals 0. It will be the second equation, and the last one will be sigma moment equal to 0. Why sigma moment? Because there is a height. There is a height of the crate and the length of the crate as well there. And all the distance, we know the distance there. Do you get it, Adam?
Yes, sir.
So for this particular purpose, right? What value that we need actually, Adam?
Could you repeat the question?
What value that we need from the second free body diagram, which we need to use in the first free body diagram?
N2, sir.
Only N2, right? So in that case, what equation that we're supposed to use in order to solve for that?
Sigma M.
Yeah, sigma moment at which point?
A.
At A equal to 0. Yes, correct, Adam. Okay, sigma moment at A equal to 0. Sigma moment at A equal to 0. Using that, what equation that we can get? With that can we get from there?
Assuming it's positive counterclockwise, 900 times
900 times
1.2 is it cos 5 degrees.
Cos 5 degrees. So remember about because what we need to find out is the wait, this one is the center is here. Okay, 1.2 is the length from here to here, right?
Yes.
Okay, and for this one is this. The length is 1.2, but remember this one is going like this. So what distance that you want to find?
Oh, 0.6.
0.6. What is 0.6?
Because it's
Oh,
half of
because it's
1.2.
okay. It's half. It's half of the 1.2. And what else?
Cos 5 degrees.
Cos. Why suddenly cos?
Not sure, sir.
Oh, because this one, right? You have to find this distance, right?
Yes.
How can we find that distance? It's not that simple. That one, because remember, right? 900 Newton is happening at the center of the crate. Okay, 900 Newton is happening at the center of the crate. So the distance from here to here is correct. That one is 1.2 meters. But the distance from here to here, which you are trying to find just now, the distance is not is not 0.6 meter. Do you get it?
Can we do 0.6 plus what is that? 0.35.
Yes, correct.
Cos, wait, sine 5 degrees.
0.35. 0.35.
Sine
Actually, that
5.
one is not sine, right? That one is not supposed to be sine. It's supposed to be tangent.
Oh, yeah.
Okay. So for this one, the length of the small one like that, the length from this to this, okay, is supposed to be L there, right? Is supposed to be 0.6 plus 0.35, okay, 0.35 tangent 5 degrees. Okay, sorry. Yeah, correct, right? Tangent 5 degrees. So that's the L there. Okay, so you mean 900 is supposed to be multiplied by that, 0.6 plus 0.35 tangent 5 degrees. What else? Multiply by just now cos 45, right? Yeah, cos 50, cos 5 degrees, right? Hello?
And then, sir, sine 5 degrees.
Correct, right? Yeah, multiply by cos 5 degrees, right?
Yeah.
Okay, then what else that we have there? Sigma moment at point A.
N2.
Minus, right? Minus N2.
Yeah.
Multiply by?
N2. Could we just treat N2 and F2 as R, sir? Would that be easier? Or just treat it as N?
Separately, because we draw it separately. So N2
Okay.
here multiply by 1.2 meters, right?
Yes.
Multiply by cos 5 degrees.
Yeah, cos 5 degrees.
Okay. What else that we have there?
0.4 N2.
Yeah, 0.4. Supposed to be plus or minus? Plus, right?
Yes, plus
0.4 N2 multiply by
1.2 sine 5.
meters sine 5 degrees equal to 0. Okay. Using this, we will be able to find the value of N2, right?
Yes.
Okay. What is the value of N2 then? Hello, Adam?
I'm calculating, sir.
Okay.
X 1.2. I got 490.1.12.
Okay. 419.1.
90 90.12.
90.
Yeah.
90.12.
Yes, if I'm not mistaken.
Okay. The value is supposed to be quite close to that. So 419.12 Newton. Okay. So the next thing was we supposed to do, Adam?
I'll move on to the wedge.
Okay, to the wedge. And for the
Since
wedge,
we
it's supposed to
know-
be a point load, right? So we cannot use sigma moment anymore. So in order to find out for P, what we're supposed to do there?
sigma Fy, sigma Fx.
Sigma Fy and sigma Fx. Okay, using sigma Fy equal to 0 for the first free body diagram, what we're supposed to have there?
P sine 10
and yeah, sine 10 degrees. What else?
minus N2
Minus N2. Then
plus N1
plus N1.
cos
10 degrees, right?
10 degrees, yeah.
Then minus
plus F2.
F2.
Oh,
No, F2 is not necessary. F2 is horizontal.
Perpendicular, yeah. Minus F1 or 0.4 N1.
Okay, 0.4 N1. Okay.
Cos 10 degrees. Sine 10 degrees.
Sine 10 degrees. That one, right?
Yes.
Okay. N2, we know the value. N2 is supposed to be 490.12. Okay.
Yes.
For this one, we still cannot solve the problem. So we have to use sigma Fx equal to 0. Sigma Fx equal to 0 there. What we will have there is what?
P cos 10 minus F 0.4 N2 minus F1
0.4
N2.
Okay, 0.4 N2 minus
N1 sine 10
sine 10 degrees
minus 0.4 N1 cos 10.
0.4 N1
Cos 10.
cos 10 degrees equal to 0.
Yes.
Okay. Using this equation, these two equations, okay, we will be able to find out for the value of P, right? Using the bottom equations, okay. Using this two equation, we have to use we have to calculate for, we have to do the substitution or elimination to solve for N2 and N1. Sorry, to solve for P and N1.
Yes.
Anyone here able to solve for this one? What is the value of P there? basically, this is the things that we have to solve. There are two unknowns, P and
I got 98.73, sir, for P.
P. Yeah. What is the value?
98.73.
Newton. Okay, thank you very much, Adam.
Yeah.
So that's the P value that we're supposed to have there. Okay, thank you very much, Adam.
You're welcome, sir.
Okay, so there are several other problem example there, but the way to solve it is quite close to that. You have to draw the free body diagram of each. We have to draw the free body diagram of the wedge itself and the mass itself. Okay. Normally, we're supposed to solve for the mass first. After we solve the free body diagram of the mass, then we can go to the free body diagram of the wedge to solve for the force, like that. This is another equation and another example. Quite close to that, I will not discuss this in detail because this one is quite close to what we had before. Okay. And one thing that you're supposed to remember is the coefficient of static friction is you're supposed to use the correct one. So for this one, this surface and this surface we have a 0.4 as our mu s. Then for this one, for the incline here, this particular surface, we're supposed to use mu s equal to 0.7. Okay. This is another example. But for this one, it's supposed to be the pulling out force instead of the pushing in force. So, but it's more or less the same. What you're supposed to do is to draw the free body diagram. Okay, what you're supposed to do is to draw the free body diagram. For this one, I think I will not solve it, but just finish drawing the free body diagram. Hello, Irfan? Okay, I think I will try to draw the free body diagram for this one. So, as I told you from the beginning, the surface, the normal force is supposed to be following the surface. So for this one, okay. So for this one, if you want to draw the free body diagram of the wedge, it's supposed to be like this. Okay, for the wedge, right? It's supposed to be like this. There is a pulling force P there. There is a pulling force P there. And beside that, there will be a normal force at C and normal force at P. And the normal force is supposed to be perpendicular to the surface. The surface that we are talking about here is the surface of the wedge, because for the mass, the surface is not the surface, but for the mass, the contact is happening at a point like that. So we don't have to calculate for the we have to follow the surface of the wedge in this case. Okay, in this case at C there will be a normal force going up, normal one, and then friction force is supposed to be going to the left because it's a pulling the force P there is pulling the wedge out. So there will be a friction force going to the left. Okay. Friction force 1. Okay, the mu s there. The mu s there is supposed to be 0.3. So F1 there, I can replace it by 0.3 and 1. Like that. At P, as I told you, the normal force is supposed to be perpendicular to the surface, and the surface that we're supposed to use is the surface of the wedge. So it's supposed to be perpendicular to the wedge. Yeah. So the force is slightly slanted. It's supposed to be N2. And the friction force is supposed to be parallel to that surface. This one is the friction force, F2, which is 0.3 of N2. Like that. So that's the free body diagram of the wedge. And if we take a look at the free body diagram of the mass, so this problem is quite close to the problem that we discussed before. So if we take a look at the free body diagram of the mass, it will be like this. Okay, at A, so there will be weight in the middle, 5,000 Newton. Then there will be normal force and friction force with the direction opposite to that. So the normal force is supposed to be going up like this. Normal force 2, and the friction force is supposed to be going like this, slightly slanted, 0.4 and 0.3 and 2. Then at A, because it's center of rotation, there will be AY and AX, like that. Okay, there will be there are three unknowns there. We can solve this using sigma fx equal to 0, sigma fy equal to 0, and sigma moment equal to 0. But the one that we need to solve is only this N2. So we can solve it using sigma moment at point A equal to 0. After we solve for N2, then we can go to this particular free body diagram. Okay. After N2 is solved, then we can solve for P that way. Using sigma fx equal to 0 and sigma fy equal to 0, because we're supposed to calculate it using point O. Okay, this is the way to solve this particular problem because it's quite close to the problem that we talked about before, this particular problem. This one and this one is quite close. It's more or less the same. This is the problem that I will give it as your homework. So please check the MS team. I post the homework there. And the deadline is on Monday because I already give the homework from, I believe it's on Tuesday. So you're supposed to submit the homework by Monday 10 a.m. Okay, this Monday 10 a.m. and this one of your homework. Okay. Wait, let me share for the homework. Yeah, this is your homework. Okay, so there are two problems of the dry friction. Two dry friction problem. This is the first problem of the dry friction. This is number one. This is your homework number one. Then another problem of dry friction. This is number 2. And number 3, 4, and 5 is about the wedge. And for your information, number 5 here is the last year exam problem. So the level of the exam problem in the friction, it will be quite close to that. Okay, those are the homework. And you have to finish it before Monday 10 a.m. and submit it via MS Teams. The link of the submission is already there. Okay. About this, is it clear enough? And remember that for the exam, for your final exam, okay, for your final exam, the topics that will be covered in your final exam is all the topics from the beginning until the end. So everything, including wedge as well. So dry friction will be there in your final exam, wedge will be there in your final exam, and all the topics which were covered in the second midterm exam will be there in your final exam, and the topics which were covered in the your first midterm exam will be there as well in your final exam. So all the topics will be there in your final exam. Okay, so please prepare well for your final exam. Okay, so please prepare well for your final exam. And your final exam, based on the information that I got in the
Sir?
Yes.
How many questions will there be for the final exam?
Maybe 3, maybe 2, depends. Yeah, it's between 2 or 3. Normally it's between 2 or 3. Okay. So your final exam will be held on, wait a minute, this one, Thursday, 20th of May. So around 2 weeks from now. Okay, Thursday, 20th of May. About this, is there any question about wedge and your final exam?
How many questions there will be in the final exam?
I answer your friend already. It's either 2 or 3 questions.
Yeah, I'm sorry, but because it's like 3 questions and 2 hours, it is rarely to like internal forces with diagram to be out.
It will be there as well. So please prepare well for that as well. So internal force can come out, frame can come out, friction most likely will be there as well, wedge may be there as well. So everything can come out. So it depends on the problem that given there in the exam. So there is no limitation for the final exam.
Okay, but thank you very much for your answer.
Is there any other question?
Sir, I have a question. For homework number 1, how is the normal force? What's the direction for the normal force, sir?
Homework number 1, the definition of the normal force. What do you think then? I think I already explained clearly about the normal force, right?
It's perpendicular to the surface. So when
which one of those that has the surface? So I mean, we have 2, right? Wall and ground and the ladder. Okay. So which one? Which from those 3 that has a surface there in the contact? The ladder. Okay, the ladder. The contact is in the shape of a point, right, Matthew?
Yes, sir.
So the surface is supposed to be perpendicular to either the wall or the ground. Depend which point that you are talking about. If you are talking about A, that is supposed to be perpendicular to the ground. If you are talking about B, then it's supposed to be perpendicular to the wall.
So the normal force will be at point A will be parallel to the y-axis. Yeah?
Yep, correct. At point B is supposed to be parallel to the x-axis.
Okay.
Okay.
So if I draw the free body diagram of AB fallen down, the normal force will have an angle of theta. Yeah?
If you are drawing the free body diagram of
AB,
okay.
when it's
yes,
okay.
correct. Yeah. So all of you must remember, okay, when we talk about friction force, the one that has a surface, we have to so if you take a look at the friction between those two, right? For example, like this, at A, the ladder, the point, the contact point for the ladder will be a point like that. But the contact point for the ground, okay, if it's slide around, it will be a surface. So that's the one that will be your reference. The one that have the surface will be the reference. Okay. So for this one, the surface will be the wall at B, and for A, it will be the ground. Okay. So whenever we have a point to surface contact, okay, like this, right? Like this number one. So the ladder will be a point at A, okay, and the ground will be a surface at A. If you have a point to surface contact, okay, the reference of the normal force is supposed to follow the surface, always like that. The same happens for this one, the previous problem that we are talking about. This one is point to surface as well. Wait a minute. Okay, this one is point to surface as well. The wedge there, the contact at the wedge, it will be a surface because it can slide around. So it will be the surface of the wedge, upper surface of the wedge. But for the concrete, right? So for the mass, this one, what is it? A mass, yeah, stone, for the stone, right? For the stone at point B, whatever happened there, okay, even though the wedge is sliding around, okay, the contact at point B there for the stone, it will be a point. Okay, so it's point to surface contact. So in this case, the reference for the normal force you're supposed to be following for the surface, in this case, is the wedge surface. So you have to think about the if there is a sliding around there, okay, which one is the surface, which one is the point? If we have a point to surface contact. So after you determine which one is the surface, then choose the surface as the reference for the normal force. Do you get it, Matthew?
Yes, sir. Yes, sir.
The same for this one as well. Okay. Anyone else here having any question?
Why is this 0.35 than 5, sir?
Sorry.
Why is this one the distance of the weight to A is 0.6 plus 0.35 in 5?
Because just now if we draw the it's about geometry, Matthew. So you can see, right, the distance there, the weight is supposed to be from the center, right? This one. The weight is supposed to be from the center here, right?
Is 1.2 the horizontal direction? Horizontal distance, sir?
Yes, 1.2 is horizontal distance. But just now, what we want to find is the distance from this to this. What we know is the distance from this to this, which is 0.6 meters, half of 1.2 meters. So we have to calculate for the small distance here, right? The small distance there is supposed to be 0.35 tangent 5 degrees. Correct, right? Because this one is 0.35 and this one is supposed to be 0.35 tangent 5. Do you get it?
Yes, sir. Even though it's not specified on the question, the center of gravity is there, sir.
The center of
okay
gravity.
to assume...
Yeah, no, this one you can see. 90 kilogram uniform free.
Oh, I see.
When it's uniform, it's supposed to be exactly at the at the center of the grid. Okay, you get it?
All right, sir.
I think that's all, right? For our discussion for this particular wedge. Okay, and that will be our last discussion as well. So today's will be our last class. So after this, what you're supposed to do is to prepare well for your final exam. Okay, remember that your exam will be happening on the 20th of May, Thursday, 20th of May. So please prepare well. Okay, the topics which will be covered in your final exam will be all the topics that I already taught you. Okay, from the beginning until this switch. Okay, I think that's all. Don't forget to mark your attendance. That's all for today's discussion as well. Okay, I think that's it. Stop share. So please prepare for your exam, and that's it. Okay, thank you very much for listening in this one semesters, and we will I think I will see you again next semester. Most likely you will still be there in my other class, especially the mechanics of materials for next semesters. I think that's all. Okay, thank you very much for listening. See you guys. Please study well for your exam.
Thank you, sir.
Terima kasih banyak, Pak. Sampai jumpa di semester selanjutnya.
Thank you so much, sir.
Thank you very much, sir.
Thank you very much.
Terima kasih, Ojan.